In this video, we begin our review of the principles that we learned in basic chemistry. We're going to focus on the narrower portion of the subject that really is relevant to organic chemistry, because that's what we're going to be studying this semester. And so in the first half, we're going to talk about just the basic ideas of structure of matter. And in our second video, then we'll even add in a few other concepts on molecular structure. So the first thing we learned back in basic chemistry is that matter is anything that occupies space and has mass. And of course, energy is not matter. Energy is the ability to do work, and heat and light are two examples of energy, and they don't occupy space. They don't have rest mass. And so these are two things that we work with, matter and energy. So now, looking at the concept of matter, there's all sorts of matter around us, and we have one simple breakdown to start off with, and that is a simple substance versus a more complex substance. So what do we mean by this? Well, a pure substance has the same composition throughout. Now, if you have a complex substance, many complex substances can be composed of multiple simpler substances. So then the question is, what actually makes a simpler substance? Well, it's pretty simple. It's based on mass. If you have an object, and that object is composed of multiple substances, and you can remove some of those substances, and they have their own unique sets of properties, and they weigh less, of course, than the starting mass of your overall material, you have broken this down into a simpler substance. So a super simple idea would be, imagine you've got your action figure G.I. Joe. So let's take the G.I. Joe and tear it all apart. So we're going to pull the arms and the legs and the heads off. So the head's off, the arms and the legs are off. And you remember there are little, if you ever had one of these, there's like little stretchy elastic bands holding the arms and legs on. And there's a little metal hook in there. So I can pull all the metal hooks out that are inside my action figure, and I can set them aside. And all those metal pieces have the same property. They're electrical conductors, and they're a little bit hard. So those are simpler substances, and they, of course, weigh less than the original G.I. Joe weighed. And then I can take my elastic bands, and I could take all the rubber that makes up the G.I. Joe body and legs, and that would be another substance. So the basic idea, simpler substance, it's based on mass. A starting material or structure or substance is broken down into samples of lower mass that compose that overall substance, and those lower mass, smaller amounts of substance each have unique properties. So that means that we produced simpler substances from a more complex substance. Now we can do this in a chemical case, and we talked about this back in basic chemistry. Let's imagine that we have powdered sugar. Okay, if I take powdered sugar, and let's say I take 20 grams of powdered sugar, and I immerse it in sulfuric acid, we'll find out that we could take the sulfuric acid out after we're done, and we would end up having converted the sugar into water and carbon. And out of my 20 grams of substance, maybe 11 or 12 grams, I'd have 11 or 12 grams of water and maybe 8 or 9 grams of carbon in that left over from that. Okay. Now the carbon, of course, is a simpler substance, and the water is a simpler substance. So those are simpler substances than sugar. Now it turns out carbon, as we'll see in a moment, and if you remember, carbon is an element, so we can't break that down any further. But the water then, if we run electric current through it, we can turn that into hydrogen and oxygen. And maybe out of my 12 grams of water, I end up with maybe, 10 or 11 grams of oxygen and 1 or 2 grams of hydrogen. And the hydrogen and the oxygen can't be broken down any further. So those are the simplest substances that we would have in this system. Okay? So now, as we think about substances, we've talked about simpler and more complex. Here's a hierarchy that I've laid out, and you have this table from your notes back in basic chemistry. And this lists all materials that we know of in terms of hierarchy of complexity. And at the top of this list are the most complex substances. At the bottom are the most chemically simple substances. So the most complex substances we have are heterogeneous mixtures, okay? And so, for example, our GI Joe would be a heterogeneous mixture. It's composed of multiple substances, and we can physically separate out all the different parts, okay? Now, a homogeneous mixture is something that is uniform throughout its composition, but it still is composed of multiple substances. So, for example, the metal, which might be an alloy in that G.I. Joe action figure we had, maybe that metal alloy is composed of maybe zinc and copper in terms of to make brass fittings. I'm not sure if they're brass or not, but we can physically separate those by heating them up and melting them and kind of separating them that way. Now, within homogeneous mixtures, you can have compounds and elements within those. And compounds are the next most complex systems. And then the simplest systems are elements. So heterogeneous mixtures have multiple phases and multiple components. So an example would be, for example, oil and vinegar salad dressing. You shake it up and it seems to mix together, but you'll notice that there are oil droplets and water droplets, and they're separate phases. Okay, so most things you come across are heterogeneous mixtures. Your G.I. Joe, if you have a cell phone, if you have food that you've made. Homogeneous mixtures are simpler. They're uniform, they're a single phase, but they have multiple components. So for example, if you had a bottle of Kool-Aid or a bottle of Gatorade, that would be a homogeneous mixture, because as you look at it, it's the same composition throughout. It's a single phase. There's only one composition throughout, top to bottom, within the bottle. But there's multiple components. So Gatorade has the green dye that's added to make it green for Gatorade, right? The original Gatorade. It's got sugar in it. It has salt in it. It has, it's got other substances present. It's, got maybe a little bit of citric acid to give it a little tart flavor as well. Now, compounds, these are single substances. They are pure substances. They can be made pure. So, for example, the water in the Gatorade or the water in the Kool-Aid, that would be a single substance. The sugar, the salt, the dye, the citric acid, each one of those components would be a compound, and they are single substances. And then finally, if we break those compounds down, we can find the composing elements that make them up. And those are the simplest single substances that are known in the universe. And we'll talk about the smallest particles that make these up a little bit later. So the pure substances, they have uniform or the same chemical composition throughout and between different samples. And there are two types of pure substances. Now, the simplest we saw a moment ago is an element. And an element is a substance that can't be broken down into simpler substances by a chemical process or a chemical reaction. They're the simplest chemical substances. And then also we have chemical compounds, and they're composed of two or more elements that are combined in definite proportions. So they have very specific ratios by mass of each element present, and each compound has its own unique set of physical and chemical properties. Now, elements, it turns out that an element is a substance that can't be broken down by a chemical reaction. All the known elements are organized in a periodic table, and we'll show that in a moment. Maybe you remember the periodic table we looked at. And it turns out that there are 90 elements that occur in measurable quantities in nature, or I would say significant quantities. There are 90 naturally occurring elements, and then there are some others that are man-made. So here's our periodic table, and you can see in this periodic table there are 118 elements listed. Each box represents its own element. Typically elements, and in fact always elements, their symbol consists of one or two letters. Typically they're in the element name, or they're in the Latin version of the name. And so you can see each of these boxes, there's some numbers, and we'll talk about the numbers in just a moment. But you can take, for example, element number 6 is carbon, and that symbol is C. That's in column number 14. It's called group 4A. And we're going to spend a lot of time on carbon in this course. Other elements are hydrogen, that's element 1 with an H. Nitrogen, that's element number 7 with an N. Calcium is element number 20, and that's Ca. Oxygen is element number 8, and that has the symbol O. And chlorine, that is element number 17, and it has the symbol Cl. And if you look through this, if you're just curious, the naturally occurring elements go up to number 92. Number 92 is uranium, and uranium, of course, occurs quite a bit in nature. There's lots of it all around the Earth. And so you say, well, there's 92 elements in nature, but it turns out two of the smaller elements, that is element number 43, that is Tc, that's technetium, and element 61, that's Pm, that's promethium. Those two elements, it turns out, are unstable. They don't occur in nature in any measurable quantities. They're radioactive and they fall apart right away. Turns out element 43, that's in column 7 or column 7b. Technetium is used for certain biomedical applications because it can work as a radio tracer. Now, when we look at the elements, there's lots of ways to classify them, but one of the most important is, just based on their physical and chemical properties, very grossly, there's 3 groups. There's the metals, the nonmetals, and the metalloids. Now, metals you're familiar with. You've handled metals before. If you have, for example, a screwdriver, it's typically will have a metal shaft on it that you use to turn the screw. Nails are typically made of metal, bicycle frames, and so forth. And most elements are actually metallic or metals. And you can see this slide here shows you some examples, like chromium is used in a lot of places, like for coatings on metal bumpers, used sometimes in bicycle frames. Copper, of course, is used a lot for its electrical properties. It's a very good electrical conductor. Cadmium, hopefully you haven't been around cadmium too much. That's a toxic metal. It's like mercury. It's just it's right next to it in the periodic table. And of course, lead and bismuth. And so these are kind of typical. They tend to be silvery, but not all of them are silver. They tend to be silvery and tend to be, bendable and stretchable, and all of them except for mercury are metals at room temperature. So those are solids at room temperature. So those are the metals. Now the nonmetals are different. They have a wide range of properties. We'll look at them in a moment, but they tend to be all over the place in terms of their phase. So carbon, for example, is a hard, brittle solid. Iodine is a solid material. Sulfur is a solid. It tends to be a powder. That's the way you encounter it usually. Bromine is a liquid. That's one of the 2 liquid elements. And then there's a group of them that are gases: hydrogen, nitrogen, oxygen, fluorine, chlorine, and then all the noble gases. And we'll look at nonmetals a lot this semester. Turns out nonmetals make up all of organic chemistry. And then there is a small cluster of elements. We call them the metalloids. Sometimes they're called semimetals. They're halfway between metals and nonmetals. And they're all shown here. boron, silicon, arsenic, antimony, tellurium. There are a couple of others, germanium as well. And so as we go back to our material complexity, we recognize that when we have an element, there is a smallest amount of element that we can have that will still retain its properties. And that's what we call an atom. So if you have an element and you cut it in half, you still have two uniform pieces and they both have the same properties. So those are not simpler substances. They're simply smaller amounts of a simple substance. And you can keep doing this until you get down to the atom level. And once you've got an atom, you can't cut that in half anymore using chemical means. And it turns out chemical compounds show similar behavior, and their smallest particle is a molecule. And we'll spend a lot of time on molecules this semester. So now next we're going to go back to atomic theory to think about atomic structure. This is going to be very important for us this semester. So now remember Dalton's postulates. He had 4 postulates, and then we updated them with the addition of some modern physics measurements. And Dalton's first idea was that all matter is composed of atoms. And an atom turns out to be the smallest body that retains the unique identity of the element. Next up, atoms of one element can't be converted into atoms of another element in a chemical reaction. And in fact, that's never been observed, and there is reason to believe it never will be observed. Atoms can't be converted using chemical processes. We can convert them using nuclear reactions, and that gives us insight into how much energy is involved, and it's far more energy than is involved in any chemical reaction. Next up, atoms of an element have the same number of protons and electrons. And it turns out that is what determines the properties and chemical behavior of an element. It's the number of protons that are present. And it turns out that Dalton had the idea that it was based on mass, but we updated that, and we recognize it's based on protons and electrons. And there are isotopes of an element that can have the same number of protons and electrons, but they differ in what we call neutrons, and we'll talk about those in just a moment, and thus they'll have a different mass. Finally, compounds are formed by chemical combination of 2 or more specific elements in specific ratios by mass. So here's a picture of an atom. It's a kind of a cartoon structure. An atom is an electrically neutral, and we look at it as a spherical entry. It's composed of a positively charged nucleus in the center. So the little kind of crunchy center contains the protons and the neutrons held together very tightly using the strong nuclear force. And then they're surrounded by the electrons, and there's a cloud of electrons. And in this slide, then the soft red outer part of the atom is the electron cloud. And we'll think about electron clouds a lot this semester. So the nucleus contains all the positive charge, and then the outside is the electrons. And it turns out electrons can be added to or subtracted from an atom, and you still have the same atom. So it turns out the proton is the truly defining structure. Now, in terms of sizes, typically atoms are approximately 10 to the minus 10 meters across. So it's about 1/10 of a nanometer. The nucleus is very small, and they're typically 5 times 10 to the minus 15 meters across. This table then provides us a summary of the particles that make up the atom. And we're not going through all the experiments that demonstrated the existence of protons, neutrons, and electrons. I'll let you go back and review that yourself, but this is just a summary. The protons are positively charged and the neutrons are uncharged. They're in the center of the atom and the nucleus, and their size is approximately 1 atomic mass unit. Their masses are shown here in grams. So these are located in the nucleus. And then the electron is negatively charged. That's on the outside. Its mass is approximately 2,000 times smaller than that of the proton or of the neutron. When we look at each individual element, we have a few different ways of representing these. And so here, this box, the little gray box in the center, this represents like one of the boxes inside the periodic table. The X would be your atomic symbol for your elements. So for example, for carbon, that will be a C. For hydrogen, it will be H. For fluorine, that will be F. Then in the upper left-hand corner of the symbol, we put the mass number. That would be the specific isotope that we're looking at. And that's going to be the number of protons plus the number of neutrons. And we typically don't do this as chemists, but nuclear chemists and physicists in the lower left-hand corner will write down the atomic number. It turns out that that's redundant because if you know the symbol, you know the atomic number. So for example, carbon always has 6 protons exactly. And any atom that we have ever seen in the universe that has 6 protons is a carbon atom. There is no variation to this law. So the number of protons defines the element. So for example, if you have an atom that has 8 protons in it, you know without a doubt it is oxygen. And in fact, one thing that's interesting is you won't ever end up with 8.1 protons or 8.2 or 8.5 protons or 7.8. You always have an exact number of protons. So you'll always have 8 protons exactly in an oxygen atom. Each hydrogen atom will have 1 proton in it. So coming back and looking at our periodic table, let's take some examples. And I want you guys to do this as a practice for yourself. So here are 6 isotopes. Iron 56, carbon 14, natrium 93, lead 207, chlorine 35, and chlorine 37. And I've given you the periodic table, and what I'd like you to do is to determine the number of protons, electrons, and neutrons in each of these 6 atomic isotopes. So let's take as an example, iron 56 is our first case. So now if you have iron 56, I want you to look on the periodic table. You can see that iron is element number 26. So what does that tell you? That tells you that it will have 26 protons and 26 electrons. And in this case, since it's iron 56, its mass number is 56, we can calculate the number of neutrons. So protons plus neutrons equals 56. You've got 26 protons. You can calculate the neutrons. So 56 minus 26 gives you 30. You now have calculated the number of neutrons. So iron 56 has 26 protons, 26 electrons, and 30 neutrons. Now, you should pause the video and do the same for the next 5 elemental examples. Carbon 14, natrium 93, lead 207, chlorine 35, and chlorine 37. So stop the video and you do the calculation now. Okay, now that we're back, let's go through, I'll put up the answers for each of these. So here we see we had already done the iron 56 case, 26 protons, 26 electrons, and 30 neutrons. Carbon 14, which turns out to be a radioactive isotope of carbon. If you look at carbon, it's always got 6 protons and 6 electrons. And so we have to have 8 neutrons for this system. Now, one thing I'd like to point out here, this example is only for the neutral atom. We're going to see later on that when you have ions, and you may remember this from back in basic chemistry, you can have you can change the number of electrons. So for example, if I had carbon as a positive ion, I'd have fewer electrons. I'd have to lose electrons to give it a net charge. Okay. Now continuing on, next up is niobium. You'll see that's in group 5. So if you go down to the second row of group 5, you have niobium, which has a atomic number of 41. So there's 41 protons, 41 electrons, and then 93 minus 41 gives us 52 neutrons. Next up, we have lead-207, and you can see lead is over here in group 14, group 4A, and it's got a mass number of, in this case, 207, an atomic number of 82, so we have 82 protons, 82 electrons, and then 207 minus 82 gives us our 125 neutrons. We can do this for chlorine, and you can see chlorine is element 17. So for both isotopes, 35 and 37, there are going to be 17 protons, 17 electrons. And for chlorine 35, then we have 18 neutrons, while for chlorine 37, we have 20 neutrons. So hopefully you're comfortable with that. That's kind of a quick review on atomic numbers and atomic masses. Now let's go on to chemical compounds. A compound is also a pure substance, just like an element, but a compound is composed of 2 or more elements that combine chemically in definite proportions by mass or by mole. A compound has properties that are different from each of its component elements. And so here's, for example, iron pyrite. That turns out to be a chemical compound. It's sometimes called fool's gold if you've ever seen it before. It looks gold, of course, but of course it's not malleable or ductile like iron is. So if you hit it with a hammer, it doesn't bend out flat and behave nicely like that. Fool's gold, iron pyrite, is, in our naming from basic chemistry, we would call this iron 3 sulfide. That is a chemical compound. It has a unique set of properties. Now, if I take iron and sulfur and just mix them together, I don't heat them up. That's shown on the right-hand side. And you can add as much iron or as little iron as you want, and you just have a mixture. It's not a compound. It's only when I heat up these two substances that I end up producing iron pyrite. Now, next up, we can think of a couple of more chemical compounds, and the first one is water. Water is a compound with a chemical formula H2O. Now we can break it down by running electric current through it. And if we do that, then we see that hydrogen and oxygen are produced. And that's what's bubbling up in the upper right-hand corner. You can see the bubbles in the test tubes. Those represent hydrogen and oxygen. And the test tube on the right is oxygen. The test tube on the left is hydrogen. And you notice that the volume on the left side is about twice as big as the right side. That's because we have 2 hydrogens for each oxygen. Another chemical compound is sand. Now, sometimes the sand you come across has other impurities, but really high quality pure sand is basically composed of a compound called silicon dioxide, and it has a chemical formula SiO2. There are many classes of chemical compounds, but the biggest classification scheme is the ionic and the molecular chemical compounds, and that's the one we're going to focus on the most in this slide, and mostly for organic chemistry. Now, there are acids and bases and other types of classification schemes, but we're just going to look in this slide at the ionic versus the molecular, or equivalently we call those covalent compounds. Now, the first thing I want to mention is electrolytes, because that helps us to distinguish these two. An electrolyte is a substance that when it dissolves in water, it breaks up into ions, that is, charged particles. So if you have pure water, it doesn't carry electric current very well at all. But if you throw salt in, it will carry the current very readily because the charges can move. So the substance, when it breaks up into ions, when it's dissolved in water, this process is sometimes called ionization, or it's called dissociation. And non-electrolytes do not do this. So if you take, for example, ethanol, that's grain alcohol, or methanol, which is like wood alcohol. These are non-electrolytes. They're molecular substances, and they don't dissociate in water. Now, let's go to our classification scheme. Ionic compounds are composed of a metal and a nonmetal. And you can have more than one nonmetal, but you typically have to have a single metal and then one or more nonmetals. The metal will be what we call a cation. That is, it'll have a plus charge. It'll have lost electrons. And the nonmetal will be negatively charged. It'll be what we call an anion. It'll have extra electrons. You may remember this from back in basic chemistry. If you take a metal and a nonmetal and you react them together, the metal gives up its electrons to the nonmetal and it forms an ionic compound. And the cations and the anions exist such that overall the net charge is zero. So if I have sodium and that has a +1 charge, and chlorine, which has a -1 charge, I just need one of each. But if I have sodium with a +1 charge and oxygen or oxide with a -2 charge, I'm going to need 2 sodiums for each oxygen. So ionic compounds are also called salts, and they're the first major category of chemical compounds. We talked about them quite a bit in basic chemistry. Molecular or covalent compounds are composed of 2 or more different nonmetals. And here I've got a picture of carbon dioxide showing the carbon in the middle with the brown or black color in the center. And then on the outside of the 2 reds, those represent the oxygens. Molecular or covalent compounds don't have an overall charge. They exist in their smallest components as molecules, and the molecules contain atoms. They're the second major category of chemical compound, and we will spend almost all of our time studying organic chemistry. We'll be working with molecular compounds. This table here is kind of a summary of the properties of ionic versus molecular or covalent compounds. Ionic compounds, are salts. And if you think back, okay, you've handled road salt, or you've handled table salt, or maybe if you've worked in the chemical factory, you've come across other salts. Okay. So ionic compounds, they're crystalline solids. That means that they're ordered structures. They tend to have flat faces. They tend to make nice cubes or hexagons or very regular structures. They are hard and brittle in general. They tend to have very high melting points. They tend to have extremely high boiling points. They're generally higher density substances. And when they do dissolve in water, they form electrolytes. And if you have a pure ionic compound and you do heat it up to its melting point, 1,000 degrees, typically that will also work as an electrical conductor. Molecular compounds or covalent compounds, on the other hand, can be gases, liquids, or solids. When you go to the gas station and you pump gasoline, that's a gas. Natural gas, if you have, when you handle that, that's typically a gas. Paraffin wax tends to be a solid. When they're solids, they tend to be much softer than ionic compounds. They're lower, their melting points are lower relative to ionic compounds for the same molar mass. And they tend to have low boiling points. Their densities are a bit lower. So for example, oil floats on water. They tend to be low density compounds. And when you dissolve molecular or covalent compounds in water, they form non-electrolytes. They're not electrical conductors in their pure form. So here's 3 examples of compounds. The first one is sodium chloride. And sodium chloride is an ionic compound. The sodium is the metal, the chlorine is the nonmetal. The sodium has a positive charge, the chlorine has a negative charge. And you can see in the representation, the picture here, the big greenish balls are the chlorine atoms, and the small grayish balls are the sodium atoms. They are in a very regular cubic structure. So the positive charges are near the negative charges, and the negative charges are near the positive charges. Now, carbon dioxide can be compared to this. Carbon dioxide is a molecular compound. It's a neutral compound. It's a gas. You can see the carbon in the center and the oxygens on the outside. And for comparison, we have an element at the bottom. And this is oxygen. And it turns out oxygen is a molecular, that is a covalent element. It exists in a diatomic form. Now here's an example problem to work through. You've got 5 different chemical compounds. For each one of these, I want you to classify it as an ionic compound or a molecular compound. So stop the video and go through the 5 of these and see what you can come up with. Okay, so now that you started the video back up, let's go through each of these examples and put up the answer. First, we have CCl4. We'll see later on this is named carbon tetrachloride. Carbon is a nonmetal, chlorine is a nonmetal. 2 nonmetals means this is a molecular compound. Next up, we have CaF2, that is calcium fluoride. So we have calcium, which is a metal, you guys know that. Fluorine is a nonmetal if you look at your periodic table. So a metal plus a nonmetal gives us an ionic compound. Third up, SF6, sulfur hexafluoride. You have 2 nonmetals, sulfur and fluorine. Therefore, the compound is molecular. Our 4th compound up is a little more complex. We have copper, which is a metal, and then carbon and oxygen, which are both nonmetals. In this case, we would classify this compound as ionic because it has metal and nonmetal. But we'll see later on that the CO3 part, the carbonate part, has some covalent bonding in it. You may remember that from back in general or basic chemistry. Finally, we have water, H2O. This is 2 nonmetals. It is a molecular compound. Next up, we're going to talk about chemical equations or chemical reactions. Chemistry is really all about converting one pure substance into a different pure substance. Typically taking elements and converting them into compounds, or taking multiple compounds and reacting them to produce more complex compounds. So typically what we'll do is we'll write out a line and we'll put down a series of symbols like A, moles of A, and in parentheses P represents the phase. So A and B in this case are the chemical reactants. And then we'll have an arrow that means yielding the products, C and D in this case. And very often over on the left-hand side, we'll have in parentheses, we'll indicate the overall energy flow that occurs in a chemical reaction. Every chemical reaction involves some energy flow. Now the little A, B, C, and D, these represent the number of moles of each chemical species, and then the species are capital A, B, C, and D. When we do this, we'll very often write the conditions for the reaction above the reaction arrow. So we might have a specific temperature we need to achieve, or a specific pressure, or we need the presence of a catalyst. And it's also a good idea to write down the phase of the reaction, the reactant or the product, and we'll put those in parentheses. So we'll have solids, liquids, gases, or aqueous. And finally, the little a, b, c, and d, the number of moles of each element must be the same on the reactant and product side. And you have to show all the reactants and products. So let's go back and balance a couple of chemical reactions. So hopefully you remember chemical balancing from basic chemistry. So here are 3 chemical processes, and I want you to go through and balance each one of these, making sure that you have the number of atoms of each component the same on both the left and the right hand side of the arrow. So now you can stop the video and you can balance the equation and come on back when you're done. Okay, so here we can see our first reaction is aluminum metal plus Fe2O3, that is iron 3 oxide, and this goes on to produce aluminum oxide and molten iron. And you see in this case there's 1 aluminum on the left and 2 on the right, so we need a 2 in front of the aluminum. And for the iron we've got 2 on the left hand side and 1 on the right, so we're going to need a 2 in the front of the 1 on the right hand side. The oxygens are already balanced at 3 on each side. So here's our balanced equation, 2, 1, 1, 2. And if there's a 1 in front, we typically will leave it off, because if we don't have anything there, we know it's a 1. Next up, we have methane reacting with oxygen to form carbon dioxide and water. And at the start, we can see the carbons are the same on both sides, so that's easy to work with. Now the oxygens are out of balance. We've got 2 on the left and 3 on the right, so that's going to have to be remedied. And then we've got 4 hydrogens on the left and 2 on the right. So if we stick a 2 in front of the water to balance the hydrogens, the oxygens end up balancing nicely by sticking a 2 in front of the oxygen. So 1, 2, 1, 2 are our stoichiometric coefficients. Next up, we have a compound, we'll see later on, this compound is called ethane. If I take ethane gas and chlorine gas and I give it a little bit of UV light, we'll see that we can actually make up this compound trichloroethane. That's our product, plus hydrogen chloride gas. So in this case, in order to balance this, we're going to need to stick a 3 in front of the chlorine and a 3 in front of the hydrogen chloride gas. That's the end of this video. You can stop now, and we'll move on to our next video in just a moment.